Okay, yeah, so now for something completely different, I guess. So I'm Jo, I'm at the University of Leeds. I'm aware that Venus is a little bit outside most people's wheelhouse, so I will try and keep this sort of general interest and not go too into detail, but please do ask me at the end if you'd like to know more about anything. So, broken it already, Jonathan? There we go. Okay, so Venus is slightly smaller than Earth. It's a lot hotter at the surface though, and it's a lot more dense. It has a predominantly CO2 atmosphere as opposed to our mostly nitrogen one. But the thing that's interesting to me, and from an aerosol point of view, is that it is covered in clouds, pole to pole, day side, night side, all the time, clouds. These are made of sulfuric acid. The only thing I would like you to remember is that there are 3 size modes. You don't need to remember the sizes, but when I say mode 1, mode 2, mode 3 later, clouds. And as you can see from this image, which is approximately real color, if you can convince yourself it's slightly yellow and there are a few contrasts, excellent. If not, I'm blaming the projector. So this is broadly visible and it's featureless. Whereas if we look in the UV region, it's a very, very different story. Thank you. So these are some of the first photographs that were published of Venus. They're taken from Earth-based telescopes in 1927. And you can see we've got bright patches at the top and darker patches in the middle. And then this is a later image. This was taken by Mariner 10 in the 70s. And again, you've got the brighter poles and the darker equatorial region. And we still don't know what causes those patches. It was initially thought that this was due to SO2. So in the yellow here, this is the observed albedo of Venus. And in the blue is the SO2, and you can see they've got a very similar shape down from sort of 0.2 to 0.3 microns. But beyond that, they really start to disagree. So it was thought that there were 2 absorbers. There's SO2, which absorbs up to 300 nanometers, and beyond 300 nanometers, there's a second one, which gets called the near UV absorber or the unknown UV absorber, all sorts of fun acronyms. I'm going to stick with the near UV absorber, just to keep it nice and easy. So this is it in the black with a few different candidates in different colors, and you can see none of them fit terribly well. However, with modern technology, we can do simultaneous imaging. So there's a Japanese orbiter at Venus at the moment called Akatsuki, and it images, I think these are about 4 minutes apart, which is the best we can do for simultaneous at the moment. This is looking at 283 nanometers in the SO2 region. This is at 365 nanometers in the near UV region. And while there are a few differences, there's a lot of features between these two that are very, very similar. So you get these dark streaks and these light streaks, and there's also a few sort of angled ones down here. Now, there's 2 possible explanations for this. First is that whatever this near UV absorber is, it's chemically related to SO2. So say SO2 makes something which makes this absorber. So you've got lots of SO2, you get lots of absorption. The issue with this is that whenever you do the calculations, you work out the lifetimes and the concentrations and the rate of formation, we're 2 orders of magnitude minimum too low with any sulfur-based species that we can think of. The alternative is that when we said earlier, everything up to 300 is SO2 and everything beyond 300 nanometers is something else, that's wrong. This something else is also absorbing in the SO2 region. And of all of the candidates, and the one I'm going to be talking about and the one I've been focusing my research on, is the one that I think has the best chance of explaining that, and that is something called ferric chloride. So ferric chloride is expected to absorb at around 365 nanometers, but when you put it in sulfuric acid, like in the cloud droplets, it forms ferric sulfate. Now that's going to be at around 290 nanometers. So this would give us that correlation between the wavelengths that we need. There's a few issues with it. People have done estimates of how much ferric chloride you would need, and they come up with about 1% in every single cloud droplet, which doesn't sound like a lot, but that's huge. That's all covering the planet. And we're talking hundreds or thousands of years of iron accumulation in the atmosphere to get that sort of concentration, which, I mean, it might be feasible, but probably not. The other issue is that absolutely no one has published a spectrum of ferric chloride and sulfuric acid. There's two spectra of ferric chloride itself. They look very different from one another. So this is what I've been doing. This is one of my spectra, well, 6 of my spectra. I've taken ferric chloride and hydrochloric acid to sort of stabilize it, put it in sulfuric acid, and these are different concentrations of the ferric chloride. So down at the bottom in the red, this is pure sulfuric acid, increasing in concentration. This is what it looks like after 24 hours. This is what it looks like after a week. And you can see they're very different. So what we're seeing here is ferric chloride turning into ferric sulfate. So we can work through the different features of this and see what they all are. So on the left-hand side, there's a bit of a shoulder. That's due to the sulfuric acid. So we can broadly ignore that. It stays the same across both spectra. Then this is an Fe3+ ion. This is the ferric sulfate complex ion. And this is a suspiciously long tail. If we go back to the previous one, we have, again, the sulfuric acid exactly where it was. Interestingly, the Fe3+ peak has shifted slightly, as has the ferric sulfate peak, and it's more of a shoulder now. And instead of this long tail, we've got a distinct peak. This is our ferric chloride. Interestingly, this shift in the wavelengths of the other peaks suggests that there's actually not just ferric chloride absorbing here, there's ferric chloride absorbing here. And that's what's shifting those peak maxima. Annoyingly, that means I can't separate out the different contributions, and I can't say this is a spectrum of ferric chloride and this is an Fe3+ ion and this is this and this is that, which I would like to do. I'd like to be able to, predict the different concentrations of the different ions at different temperatures and different concentrations of the acid, and then construct what those spectra would be. At the moment, I can't do that. So what I can do is take this spectrum and compare it to observations. So the MESSENGER spacecraft took some spectra when it did a flyby of Venus on its way to Mercury, which is what the M stands for in MESSENGER. And the best estimate we have for the imaginary refractive index of the absorber based on the MESSENGER data, assuming it is mixed with the mode 1, you've remembered the cloud modes, so this is the smallest size of the cloud particles, that gives you these crosses. Now, these colored lines are the imaginary refractive indices of the spectra I took, and they're all a bit low, but we can predict the concentration of ferric chloride we would need in these mode 1 particles to match this observation, and it's 0.01%, which is significantly lower than the 1% that's previously been suggested. However, this is very much a back of the envelope sort of scaling lines. Oh, don't they look pretty? So we should probably do some actual modeling. So the code I've been using is called Socrates. It was developed by the Met Office, and I spent my industrial placement working there with James Manners. So Socrates was developed for Earth, but it has been used by the University of Exeter for various exoplanets and for some Mars modeling. So we've been making it work for Venus. In its standard form, it treats the 3 cloud particle modes as 75% sulfuric acid. What I've done recently is I've replaced the imaginary refractive index of the sulfuric acid with my measurements of the imaginary refractive index at different concentrations. And I've done that for 3 different cases. One, I've replaced it for just mode 1, like that assumption for the MESSENGER data. A lot of previous work with ferric chloride has actually only assumed it's in mode 2. So I've tried that as well. And I've also tried all of the modes. So how does this look? Well, this solid line is what we want to see for our net flux profile. This dashed line is what you currently see for Socrates without an absorber in there. So this is downward net flux, which is net flux coming into the atmosphere minus reflected net flux. This is too low because our clouds are too reflective. Whereas when we include ferric chloride, it's looking much, much better. And interestingly, while for mode 1, we do see again 0.01%, for mode 2 or for all 3 modes, it's more like 0.001%. That's way better than previous stuff has led us to believe, and that's only actually about 10 years of meteoric accumulation. Vertical transport on Venus is very slow, so this is by no means unreasonable. If there's also some emission from the surface, or there's a way of cycling ferric sulfate back to ferric chloride, it could be even less, which is very, very exciting. So what would I actually like you to remember from this? Well, first of all, I would like you to remember that Venus is very, very fun and very interesting, and we should all study Venus. From a slightly more scientific point of view, there is absorption on Venus that nearly 100 years later, we can't explain. I think ferric chloride could be a very, very good candidate for that, though I still have a lot of work to do. I'd like to say a big thank you to the research groups in Leeds, and especially to one of the postdocs, Sandy James, who is very useful at converting my physics knowledge into actual practical chemistry knowledge. Thank you very much for listening.